found recently and we investigated recently, where we have evidence that there is a very nice or very interesting phase diagram and very interesting property, namely being a new cerium-based heavy fermion system close to a quantum critical point, which might be of quadrupolar nature, and further on, which might be also a new heavy fermion superconductor. So the main actor here in this story is Seung-Young Kim, who is a postdoc working in my group, because he was able to grow the single crystal of this compound, which makes the basis for all the measurements. So all the measurements I will show were done, or most of the measurements were done in the low temperature group, which is headed by Manuel Brando, by Jacinda Banda, Daniel Hafner, and Dongyun Yang. So work, and some work was also done by Ulrike Stockert on the thermopower. And so all the work I will show has been done in our institute yet. So I will first go a little bit through basics on cerium magnetism to get the important point in this compound. So cerium has one f electron. Because the f electron have a very small radius, this leads to a strongly localized 4f moment. Because one has a very large spin-orbit coupling, one has to apply Hund's rules. So the total the good quantum number is the total angular momentum g, which is equal to total s plus and minus s. Cerium 3 plus, we have L equals 3, s equal 1/2, and therefore the lowest g multiplet is the 5/2. We have g equal 5 hands. Now in solids, one has non-spherical potential, which is called the crystal electric field, that split the multiplets. And because in cerium we have one f electron, this means we have a non-interior spin. This means we have a Kramer system, so all state in the presence of time reversion in symmetry, all states have to be doubly degenerated, and therefore we will get a splitting in 3 doublets. Only in the case of a very high symmetry cubic cases, we get a splitting in 1 doublet and in 1 quartet, and that leads, how we will see, some to new possibilities. And the overall splitting is typically of the order of 200 and 400 Kelvin. So in the case of tetragonal, for example, there are these wave function, but they will strongly depending on the real structure of the system you are looking at. So now the first excited crystal field is usually above 50 Kelvin, so usually in the range between 100 Kelvin and 200 Kelvin. Now the exchange interaction are weaker, so typical ordering magnetic ordering temperature are only 10 Kelvin, and this means if we are interested in magnetic ordering phenomena at low temperature, only the lowest doublet is relevant, and therefore one can do analyze most of the properties of the low temperature properties of cerium systems using an effective S equal 1/2 system with a usually very strongly with an anisotropic moment or G factor. And because it's a Kramer's doublet, we have only a magnetic dipole degree of freedom, and therefore we have only magnetic ordering, or has an alternative, if we have coupling with a conduction electron, then we have a Kondo screening. But now if the system is cubic and the quartet is the ground state, then we have this quartet has an electrical quadrupole moment, which provide a further degree of freedom, and we may have quadrupolar order. The problem is that there are only very, very few systems. There are quite a lot of cubic systems, but in most of them, it's the doublet, the gamma 7 doublet, which is the ground state, and therefore we have no quadrupolar order. So the system which have been very heavily investigated is cerium bohr 6 since many 30, 40 years, and more recently the system cerium 3 palladium 20 silicon 6. And both show a quadrupolar. Here is the phase diagram of the later compound, temperature as a function of the magnetic field. And if you cool down, you have first the quadrupolar transition, and then a lower temperature, you have a magnetic and antiferromagnetic transition. So quadrupolar order are very difficult to access because you don't see a signal in neutron at B equals 0. If you apply a large magnetic field, some magnetization appears and then it becomes visible. But as an experimentalist, if you have a first compound, first data, and you want to you have something like that, one very typical characteristic is that the quadruple order temperature increases with magnetic field quite significantly. And that is in strong contrast to antiferromagnetic order, which always decrease with increasing field. And that is one way to test whether one might have a quadrupolar ordering. So now I come to the next important part of the topic, namely quantum critical point. So there is a strong current interested. So one has an ordered phase at low temperature, disordered phase at high temperature. One can tune the transition temperature continuously to T equals 0. Then one gets here quantum critical point. There are very interesting phenomena here, for example, unconventional superconductivity. So there are many of this kind of system. Most of them are associated with dipolar. The ordering is associated with dipolar magnetism. There are other kind of systems, for example, charge density or structural. There are very few of them. And recently, there has also been some strong interest in quadrupolar quantum critical point system. It's an emergent topic. But also there are only very few experimental examples of appropriate compound. Most of them are with fraseolum-based compound, because in this case you have a non-magnetic doublet, for example, as a ground state, and therefore they are presently poorly studied and poorly understood. And therefore it's worth to look for further systems. So we looked at the cerium rhodium-2 arsenic-2 for other reasons at the beginning. So one of the points of this compound, it's not the standard thorium-chrome-2 silicon-2 structure, which is, for example, in the iron pnictide or in cerium copper-2 silicon-2. Instead, it is the calcium beryllium-2 germanium structure, where you just, in one of the two layers, you exchange the arsenic and the iridium position. You just interchange in an ordered way, and then you get from a body-centered to a primitive structure. The important aspect for us that you lose the center of inversion symmetry at the cerium side and also in the cerium layers. In total, the structure has an inversion symmetry, but not locally on the cerium side. So it's an old compound because it was first synthesized more than 30 years ago by a chemist who found the structure, but there was no known, the physical properties have not yet been reported. And Seng-Yong Kim was able to grow single crystals using a Wismut flux. So here it's a picture of the first single crystals we get, so quite nice phases, but quite small. Meanwhile, they are a little bit larger. That's an X-ray podal diffractogram, which confirms that we have indeed this structure and not this structure, and that the compound is pretty pure. So the first things you do if you have a new compound, this kind of compound, you look at the susceptibility, because that tells you whether cerium is 3+ or intermediate valent or 4+. And this is inverse susceptibility has a function of the temperature along the C direction and in the basal plane. And you see a very nice Curie-Weiss law. The slope is exactly or very close to what is expected for a trivalent cerium. And therefore, you know, you have essentially a trivalent cerium state. But the Curie-Weiss temperature are quite sizable. But there is no evidence for magnetic order in those data down to 2. And therefore, that is an indication that we have a trivalent cerium system, but with a sizable hybridization. And also, the anisotropy is comparatively weak if you compare, for example, with ytterbium rhodium-2 silicon-2 or with cerium ruthenium-2 silicon-2. The next step you do for such a system, you look at the electrical resistivity, because that will immediately tell you whether the 4f degree of freedom interact with the conduction electron or not. If they do not, you get a normal resistivity of a normal metal, boring. If you have a strong interaction, then you get a strong temperature-dependent scattering, and that's the typical result you observe. So the resistivity is increasing with decreasing temperature, logarithmically indicating the onset of incoherent Kondo scattering. Then you go over a maximum, and then you get a strong decrease because the Kondo sequence forms a coherent state. So that is the first very clear indication that we have a strong Kondo interaction, and that we have a low temperature formation of a coherent Kondo lattices. The first test is to do the thermopower, because the thermopower of a normal metal then the 4F are completely localized, they do not interact, and therefore they do not participate to the thermopower. You get a very small thermopower with a weak temperature dependence. In this case, you get a very large thermopower, which reflects the strong scattering of the conduction electron by the 4F state, and it's the temperature dependent is also quite typical for such a system. So you have a bump here, which is likely associated with the Kondo scale, and you have a broad maximum here, which is likely associated with excitation of the excited crystal field state at higher energy. So from that, we can already say that we have a Kondo lattice system with a sizable Kondo interaction. Then you go to the most interesting part. You look at the specific heat. And here the specific heat has C/T as a function of the logarithm of the temperature, but at low temperature, for field applied along the C direction, and here for field applied in the basal plane. So you have a large increase, very smooth increase in C/T, and this indicates that you have this is an evidence for large critical Kondo type or a large critical fluctuation. What is very surprising is that you apply 14 Tesla and you do not see any change. So the swing is so small that when we show this curve to our low temperature experts, they say, okay, you just forget to put on the magnetic field. But later it was shown that indeed there is no change along this direction for field applied and of 14 Tesla. In the basal plane, we observed also pretty small change, but then at the highest field, we see a peak here, which indicates some transition here. And just looking at lower field, it seems that this transition emerged from lower temperature upon increasing the magnetic field, so that there is something at lower temperature. So, but we found something more interesting also at lower temperature, namely what we traditionally do. We look at the 4F specific heat until very high temperature, so measuring the cerium sand, measuring the lanthanum sand, where there is no F, making the difference. That is C/T. You integrate, you get the entropy as a function of the temperature. And what is here remarkable is that there is no saturation, no evidence for saturation at RLN2. There is a saturation at RLN4. And here it's going straight through. This indicates that the first excited state is not very far above the ground state and is within the Kondo scale of the ground state. So they are both mixed, and then that we have effectively something like a quasi-quartet crystal electric field ground state. And further on, you can extract now from the entropy, this is a standard method, what is a Kondo scale, and depending if you assume that we have a doublet or a quartet, you get either 20 Kelvin or 40 Kelvin for the Kondo scale. So we can say we have a Kondo scale of the order of 30 Kelvin. Then we went to lower temperature, specific heat in the millikelvin range. So here shown as C versus T as a function of magnetic field, so between 0 Tesla and 12 Tesla. And therefore, you have a first very clear anomaly here at about 230 millikelvin at B equals 0. And this anomaly shifts to lower field with increasing field and disappears at around 2 Tesla. But if you look a little bit more closely, and that has been confirmed by looking at different crystals grown from different batches, you see there's a second anomaly here, which first shift, say, almost constant, or maybe shift a little bit down in temperature with increasing field, and then increase in temperature with further increasing magnetic field, and merge exactly with what we observed in 16 Tesla at 1 Kelvin. So which leads to this phase diagram, tentative phase diagram for B in the basal plane, and this increase until 1 Kelvin at 14 Tesla. So that is very untypical for antiferromagnetic ordering, but is quite typical for quadrupolar ordering. And this is an indication that we might have in cerium rhodium to silicon 2, it might be close to a quadrupolar quantum critical point. Then we also look at the specific heat at low temperature for field applied along the C direction. And there you see that we found that there is a huge anisotropy. So the transition at T1 moves only very, very slowly down in temperature and can be followed up to 10 Tesla, while the transition at about 350 or 400 millikelvin just slightly go down and then disappear. So we have a very strong anisotropy and a very weak field dependence for B along C. And there is the question whether that might be a consequence of the lack of local inversion symmetry at the cerium site, whether that might suppress the effect of a magnetic field along the C direction. There are some predictions along this direction. Then we look also at the resistivity, and we look at a different batches, single crystal batch, and we in all of them found a superconducting transition in between 40 millikelvin and 350 millikelvin. And we looked also as a function of magnetic field, and the slope, the initial slope is very large, so you need 0.5 Tesla, almost doesn't shift the transition. And the upper critical field is of the order of 3 Tesla, despite the pretty low transition temperature. And this is the first evidence that it might be a heavy fermion superconductivity. The problem we have is that Tc is larger, is a little bit below T2, seen in the specific heat, larger but T1. But what we observed is that this transition temperature scale with T1 for in-plane applied field. We have yet no data for B along C, that is just being done. And therefore, it might be, that would be an indication that the T1 is connected with the onset of heavy fermion superconductivity. But we have certainly to confirm that. So because what we also found, we tried a different type of crystal growth, and we found that the transition at T1 and T2 in the specific heat can be suppressed in single crystal if one change the growth condition. So we now have learned how to prepare single crystal which shows a transition and to prepare single crystal which do not show the transition. So in this sense, it's reproducible. The interesting point is that above 1 Kelvin, there is no change in the properties. So the characteristic energy are essentially the same. And this means that we have only a strong dependence of only the low temperature ordering phenomena on sample composition. So that seems to be very similar to copper to silicon 2, also on the way how one can tune that. And that is in accordance with the same system being close to a quantum critical point, because if you are close to a quantum critical point, you change a little bit the hybridization and you go from one side to the other side. But we have also to say that the residual resistivity ratio of the present crystals are rather low. We are just at the amount of 2. And therefore, we suspect that inhomogeneity is likely a source of the discrepancy between the transition observed in the resistivity, the superconducting transition observed in the resistivity, and T1 observed in the specific heat. It's normal if you have a distribution that the resistivity is well above the transition in the specific heat. So we did the first attempt to look in this problem. We did single crystal X-ray diffraction, and we found no evidence for arsenic rhodium site exchange. So this single crystal X-ray diffraction confirms the structure, and also the displacement parameter are very are normal and are almost the same for all the position, which indicate that there is no problem in the refinement of the structure. And it seems that within the resolution of the X-ray diffraction, it has a stoichiometric composition. So from this point of view, the single crystal seems to be nice. But we know that that do not exceed that you have, for example, 1% exchange. You will not see them in the technique. And we know from cerium copper to silicon 2 that this can completely change the story. And therefore, what unfortunately, in some sense unfortunately, it is clear that we need an extended long-term research to clarify the composition dependence, to look at the intrinsic properties and the nature of the transition. So we have already, there's already a proposal, accepted proposal for looking with μSR to see where we have magnetic transition and where we do not have a magnetic transition. And so we certainly need further measurements to confirm whether the superconductivity is intrinsic or not. So the question one might have, isn't a quadrupolar order in a tetragonal system where one expects completely separated doublets something very unrealistic? Because it seems to require a very strong unrealistic fine-tuning to get two levels so close that you have effectively a quartet. But that is not true, because there are already a few examples where a quasi-quartet is realized in a tetragonal system. So one system, one cerium system is, for example, cerium silver to germanium 2. Here I show the specific heat, so it is taken from this paper. It's not our own work. And just looking by integrating the transition, they obtain the entropy, and you see that you get just above the transition you have always collected RLN4. So which, in this case, the crystal electric field splitting is less than 10 Kelvin approximately. So it's possible. And it's not on, but in this case, it's clear that the transition is a pure magnetic transition. There is no evidence for quadrupolar transition. But there is one case where we found even a quadrupolar transition, namely ytterbium ruthenium to germanium 2. So in ytterbium, one has the same problem as in cerium. Instead of having 3 doublets, one has 4 doublets, but they should also be splitted in a tetragonal system, so there is no protection for a quartet. And, but in this case, we also found from the specific heat that we call it RLN2 just at 10 Kelvin. And we proposed just based on the phase diagram and also on the susceptibility that the first transition at 10 Kelvin is a quadrupolar one. And then you have a succession of 3 magnetic transition here. It has been first been confirmed by CeRh that indeed there is no magnetism here, but there is a strong magnetism here. And last year it has been shown that indeed this transition is a quadrupolar transition. So one can realize a quadrupolar transition in a tetragonal ytterbium and likely also in a cerium systems. So therefore I came to the summary of what we did. So we performed the first study of the compound cerium rhodium 2 arsenic 2. It has the special properties that there is no inversion symmetry on the cerium side and in the cerium rhodium 2 arsenic 2 layers. It's a trivalent cerium, but with a sizable CF hybridization, resulting in a strong Kondo interaction of the order of 30 Kelvin. We have a quasi-quartet crystal field ground state. For T above 0.5 Kelvin, we have a divergence over T, indicating large critical fluctuation, which are not a purely magnetic one, because they are increasing much too slowly, which are at least which are pretty sensitive to magnetic field, which could also be an indication that the fluctuation are not dipolar one, but quadrupolar one. We have 2 phase transition, one very clear at this temperature, and a second one less clear, but still very clearly present in a number of samples at this temperature. We have a very unusual Beatty phase diagram in the sense that this transition for the field in basal plane strongly increase with applied magnetic field. We have a first preliminary evidence for fermion superconductivity with the transition ratio at this temperature, likely connected with T, but that has to be proved. The transition can be suppressed by composition tuning, as expected for a system close to a quantum critical point, but we expect that this system will give us work for at least the next 5 years. And that is the conclusion of my talks, and I thank you for your attention.